Yes, okay, so now 64 for first orders, second order 17, third order 3, and fourth order 1. Okay, so the ratio calculation between first and second order 3.76, 3 to second to third order 5.67, and between 3 and fourth it is 3. So mean bifurcation ratio uh, you can calculate is around 4.14. Okay. So now based on our classification, what type of basin is this? Moderate? Okay. So if the bifurcation ratio is between 3 to 5, this is a normal drainage behavior, moderate structure influence, common range for most basins. Okay. So interpreting the bifurcation ratio results. So high structure control, a mean bifurcation ratio value of 4.1 is considered high, implying strong structural control on drainage pattern. Fault guided drainage lines are guided by faults, joints, fractures, and lithological boundaries. Tectonic activity, the basin is likely located in a tectonically active or structurally complex terrain. Restricted branching, stream branching is restricted by rock resistance or structural alignment. This pattern is typical of Himalayan basins, especially in areas with high relief and active incision where geological structures dominate drainage development. So next is this is the second exercise, hypsometric integral, that is basically measuring landscape evolution. So what is a hypsometric integral? The hypsometric integral, which is HI, is a dimensionless geomorphic index that expresses the distribution of elevation within a drainage basin. It quantifies how much of the basin's original relief remains after erosion. In simple terms, HI tells how high or low a basin stands relative to its total relief, where E mean is equal to mean elevation, E max is the highest elevation, E minimum is the lowest elevation. So HI value ranges from more than zero point 0.6, that means that is in youthful stage, 0.35 to zero point 0.6 it's mature, and less than 0.35 is old. So in youthful, high relief, steep slopes, and tonically active, if the value is more than zero point 0.6, and if it is mature, then moderately dissected, transitional, low relief, strongly eroded, and stable. So you can write the formula for hypsometric integral. Now you need to calculate the hypsometric integral. So extract elevation values, derive minimum, maximum, and mean elevation from them or topographic data. Apply the formula. Use hypsometric integral equation with extracted values. So now you can do the calculation, right? You can do the calculation in the given sheet, and the formula you need to use is this one. This is your hypsometric integral HI. So now you are given this, topographic sheet in which you can calculate the different parameters. It's basically it means mean elevation, and Emax is the you need to find the highest elevation contour, and then E minimum is the lowest elevation. So you can find these numbers in the given maps. कर लिया आपने? Just wait for others to do. So what is the value you got for HI? 0 point. Any other number? Any other value? So calculating the hypsometric integral. So extract elevation values, derive minimum, maximum, mean elevation from the dam or topographic data. Apply the formula, use the hypsometric integral equation with extracted values. So E mean is 1300 meters, minimum is 800 meters, E max is 1800 meters. So the HI comes around to be 0.5. An HI value of 0.5 indicates a mature stage of a geomorphic development. E minimum, okay. So, okay. So we can see that HI value is around 0.5. That means it's a mature, moderately dissected and transitional. Mean निकालना है. We will help you. elevation. So a hypsometric integral value of 0.5 indicate that the basin is in a mature stage of geomorphic development, lying midway between youthful and the old landscape. The terrain has undergone substantial erosion, yet a considerable portion of the higher elevation still remains. It's not showing, the screen is not showing. Mhm. So, so hypsometric integral value of 0.5 indicates that the basin is in a mature stage of geomorphic development, lying midway between youthful and the old landscape. The terrain has undergone substantial erosion, yet a considerable portion of the higher elevation still remains. So, geomorphic balance, valley incision, and slope retreat have reshaped the topography, but the basin has not degraded into a low relief surface. Both elevated uplands and moderately expanded valley floor coexist. Tectonic equilibrium, moderately tectonic activity with neither dormancy nor high uplift. Uplift and erosion operates in dynamic equilibrium, maintaining relief while steadily reducing it. In hydrological response, moderately hydrological responsiveness with discharge patterns neither excessively flashy or nor overly subdued. Sediment transport and runoff generation occurs at intermediate levels. This pattern is characteristic of many mid-latitude altitude Himalayan watersheds where structural influence is present but not dormant. So these are the different interpretations in terms of geomorphic balance, tectonic equilibrium, or a hydrological response. Now, the next uh, morphometric parameter is valley floor width to height ratio VF. So, measuring valley incision, the valley floor width to height ratio VF is an important geomorphic index used to evaluate the degree of valley incision and the relative dominance of tectonic uplift versus erosion. It quantifies how narrow or wide a valley floor is compared to the height of its bounding valley walls. So the formula is Vf is equal to 2 VFW divided by VEIT minus EV plus VERT minus EV, where VFW is valley floor width, VLD is left divide elevation, VRD is right divide elevation, and VE is the valley floor elevation. A deeply incised V-shaped valley produces a low V value, whereas a U-shaped valley yields a high VF value. So now, can anybody will tell me in a tectonically driven area what kind of uh, valley shape we are expecting? Whether we are expecting a V shape or a U shape, right? We will expect a V-shaped valley in a tectonically driven area. Okay. So this parameter will help us to understand this thing. So interpreting VF values, low VF, that means less than 1, represents deeply incised valleys, narrow V-shaped valleys with steep side slopes and strong vertical incision. Typically in tectonically active regions, areas experiencing rapid uplift and young fluvial systems, common in mountainous terrains like the Himalayas, right? So deeply incised valleys, the VF value will be less than 1. And where we have the moderate, that is the transitional valley. So in moderate, the VF value will vary from 1 to 2. Partially widened valleys that are neither sharply incised nor fully mature indicate balanced uplift and erosion with a moderately active geomorphic conditions. Represents evolution from youthful to a mature stage. High VF values, if the VF value is more than 2, wide U-shaped valleys, broad valleys floors with gentle side slopes, characteristic of old or tectonically inactive landscapes, and low relief regions. Erosional dominates over uplift, producing stable widened valleys. So if we have U-shaped, that means the erosion has taken over in that valley, and that has produced a stable and widened valleys. So significance of VF in tectonic studies, indicator of tectonic uplift. So this is also important in areas where we have a recent tectonic activity, because if the area is uplifted, and then we will have a lower VF values, signaling strong uplift and rapid erosion, making VF one of the most widely used morphotectonic indices for identifying active tectonic zones. So this is very important. Valley evolution studies, by comparing VF values across a basin or between different basins, researchers can determine various stages of valley development and landscape maturity. Complements other indices when used with the mountain front sinuosity, HI hypsometric integral, and stream length gradient index. VF contributes to a holistic landscape understanding. In hazard assessment, low VF values often have steep slopes, prone to landslides, flash floods, and strong channel instability, critical for risk management. Okay. So now you are given these problems and these calculate the VF for these valleys. So if you have a digital elevation model, using a software, if you think there is, you want to calculate, so you need to have a slice. You can take a slice of elevation and you can extract the elevation values from a digital elevation model where you want to check this valley floor width ratio VF, and then you can produce these kind of elevation graphs, and from these elevation graphs you can uh, figure out the basic parameters which are required to calculate the this VF. So now you are given the problem set, and you can calculate the VF for these uh, five profiles, and then we will discuss. And you are also supposed to write which valley you think is tonically active and which one is not. Okay. So now you can do the calculation. You can write the interpretation. What are these values now? उसका interpretation भी कर दो ना कि 1 से लेके 5 तक जो values हैं वो कैसे हैं. So once you do the calculation, you can use this table. You can use this table. If VF value is less than 1, that means it is deeply incised valley. If the value is between 1 and 2, it's mature. If it is 2, then more than 2, then it is a widely U-shaped valley. So you can this use this interpretation table to classify your valleys. Okay. So what are the values for, okay, 1, 2, 3, 4, 5. So first one, 0.2. Third, 4.39. 4.15. 1.5. 1.5. Everybody got the same numbers. Okay. So now you can classify also. This valley deeply incised means tectonically, you can say tectonically active, huh? Deeply incised. This one transitional. This one U-shaped, है ना? So no tectonic activity like that. This one, अच्छा second वाली भी 2 से ऊपर है. Okay, U-shaped है. This one transitional, deeply incised है. Deeply incised, that means tectonically active. है ना? So now you can see that by calculating these numbers, you are getting some kind of a sense that how this area is big, whether it is tectonically active or whether it is not. So we are getting this kind of numbers, and that is helping us to understand the landscape of an area, whether how it is deforming, whether it is in mature or whether it is in uh, active, actively deforming. So these were the numbers which were given to you. And these are the answers: 0.2, 2.3, 4.3, 1.5, 0.15. So these are the interpretations. Okay. So valley 1, yes, V-shaped. Valley 2 is again a little bit moderate. Third is totally U-shaped, Third is totally U-shaped. Second is a little bit U-shaped, yes. Fourth and fifth again transitional morphology. Fifth is again deeply incised V-shaped valley. So even though this looks very, this profile looks very normal, but let me put a question here. Let's say I want to build a dam in these, let's say this is a location of a dam. In which valley I need to build a dam? Which is the safest valley out of these five where we can build a dam? Which one? This is safe, and number two, this is also safe. Huh? What if I'm building a dam here because it's a V shape? So that gives us an idea that maybe this is tectonically active, or something can happen. Or maybe if the fault is there parallel to the dam, then this you can have a activity and the dam can be broken. So even though this parameter looks very normal to us, we just do calculation, but when we apply these things in life, in practical, then we get more insight into that area, you know. So what is the difference between 3 and 4? What is the difference between 3 and 4? In 3, we are getting a value of 1.3, and in 4, 1.5. So 3 is totally safe. 3 is more or less safe, right? Because it's a huge shape. It has wide width also. Yes. What about 4? So, yeah, this is a transitional and neither deeply incised nor very wide. Indicates balanced erosion and uplift, often seen in moderately active tectonic settings. It is again, it can be seen in a moderately active tectonic setting. This value is mature with moderate incision or a moderate tectonic influence. But uh, when we are considering big structures like dam, you need to see a larger area. If, even though maybe the fault is not passing through this valley, but let's say within 1 or 2 kilometer area, there is a big fault. And if you see some geomorphic markers that it is active fault, then you need to do more studies in order to understand what is the reoccurrence interval of that fault. That means if a fault is having earthquake after, let's say, every 200 years, or is it having earthquake after every 100 years, or it is like, let's say, every 50 years. So we need to understand whether this fault is active. Okay, if it is active, whether it has one earthquake in 1,000 years, then we can build a dam. Because one earthquake came in 1,000 years back, next one will come in 1,000 years. So till that, my dam is safe for, let's say, 100 or 200 years. But if the earthquake is coming within 50 years, and I'm making a dam for 100 years, then it can be a problem, right? Or then I may need to take some uh, structural design I need to design my dam in such a way that it can take the shaking, because you will have uh, shaking of the ground, and the water will also, that the water behind the dam which is also shaking during the earthquake, that will create a big impact while the earthquake is happening. So those parameters need to go into the dam design. That what kind of shaking we can expect in this area when we are building a dam. So all these are very, very crucial geological feasibilities which are done when we are constructing a dam. Okay. So, and one more point here I want to say that in the area of Punjab, we have done these morphometric analysis, and we have seen some areas where we are finding V-shaped valleys. That means that area is rapidly uplifting, and the role of active tectonic is there, you know. So it also helps to identify, and we have also find out some faults are active in this area also. So in Pinjordun, there are a lot of these active faults up there, you know. So these things are important. Like we also did this flow analysis. If you want to buy a house, let's say around Chandigarh, you want to buy a house. Maybe you had a deal. You want to check whether when the rain happens, does my house will have flood. The water is coming from all the directions. So you want to have you can do this kind of analysis simply by having a digital elevation model, and you can see whether my house is in a low lying area. If the flood comes, the water will come. So these kind of analysis are very, very important. One thing is that the flow, the flooding will not happen. Second is how far it is from a fault or a zone, and then you can also make your house a earthquake resistant house, because we are living in a very seismically active zone. The Himalaya in Himalaya, this is a seismically active zone, so we need to build our house in such a way that it is earthquake resistant. For example, in Japan, you have a lot of earthquakes coming, but in Japan they have designed their buildings so that they can take the shaking, right? So these are the things which we can keep in our mind. So next is the morphometric parameter is mountain front sinuosity. So mountain front sinuosity is a geomorphic index used to evaluate the degree of tectonic activity along a mountain pediment or a mountain alluvial plain boundary. It measures how straight or irregular the mountain front is. So this is the mountain front sinuosity, where LMF is equal to actual length of the mountain front irregular, and LS represents straight line length. And the tectonic interpretation is if the value of SMF is between 1 to 1 point, then it's a high tectonic 1 point moderate tectonic activity. um, low activity. In tectonic active regions, wall scarps and active uplift keep mountain fronts straight and sharp. In inactive regions, erosions create irregular sinuous shapes. Okay. So now in this is the conceptual model basically. So if the mountain is active, then active fault driven mountains maintain straight sharp mountain fronts by continuously rejuvenating the topographic boundary between the mountain terrain and the adjacent basins. Okay. Erosional dominance activity increases. Fluvial and mass wasting processes dissect the front, creating irregular sinus boundaries that reflect long-term denudation. So mountain front geometry serves as a diagnostic proxy for competing forces shaping active orogenic margins. So you can do this calculation, classification and geometric significance. So if the value is between 1 to 1.5 highly active, between 1.5 to 2.5 moderately active, and if it is more than 2.5, it is low activity. Okay, you so now you can do the calculation. You are given the problem set. Okay, you take some time to do the calculation, then we will discuss this. So, so what is the value? 1 to 5. So what is the value for one first? 1.07, 1.22. Okay. ठीक है सबका यही आंसर है. So first one is 1.07 है ना. Extreme basically yeah, everybody understood what does it mean actually, right? किसी को डाउट तो नहीं है इसमें माउंटेन फ्रंट सिनोसिटी है ना. So basically what is happening if there is a mountain front, right? If it is going up like this, so the front will be very straight if it is new tectonic activity, right? And if it is older tectonic activity, then lot of sediments will cause the sinus front. The mountain front will be more sinuous. So like for example, We are looking here, right? If there is a fault, which displaces this boundary like this, so this front will look very straight. If the mountain front is looking very straight, that means, you know, it has just gone up. But if this tectonic activity is very older, then what will happen? Lot of sediments will come and it will cover the mountain front and it will be more of a zigzag pattern. So just by looking geomorphologically or just by having a look at the mountain front, you can understand that whether it's very active or not, you know. And then this you can use this parameter to understand the activity of the mountain front. Okay. So I think this is the map of Kordwar area, right? Kordwar. So this example is taken from the Kordwar area. So extremely straight segment 1, which is this one. Segment 1 is showing extremely straight segment, very strong tectonic uplift, minimal erosional modification. Segment 2, highly linear active fault control. This one is again showing. Segment 3, slightly more sinuous but still very low. Strong structural control. Segment 4, 1.24, mostly sinuous among all but still in active range. And segment 5, 1.16, highly active steep segment, sharp at chronic front, preserving straightness. Okay. So this is again a kind of a parameter. By looking at it, we can try to understand how any area, the front is behaving in any area. So morphometric analysis key takeaways: stream order provides hierarchical classification of drainage networks, essential for understanding basin organization and hydrological behavior. Bifurcation ratio reveals structural control and tectonic influence on drainage patterns through stream branching analysis. Hypsometric integral identifies erosional stages and landscape maturity by measuring elevation distribution within basins. And valley floor indicates tectonic activity through valley incision measurements and morphology assessment. And mountain fronts anisotropy evaluates tectonic activity along mountain fronts by measuring boundary straightness versus irregularity. These morphometric indices work together to provide a comprehensive insight into landscape evolution, tectonic activity, and watershed management priorities. Their combined application enables systematic analysis of drainage basins and geomorphic processes. So if you have any questions, you can ask. So basically, we can use morphometric analysis, and then there is one more thing, which is like we can use remote sensing data. For example, cartograph data. Now we will do an exercise in which we will show you some of the anaglyphs. Basically, in that you can see an area, you know, in 3D. Like maybe you have seen a movie in which a 3D movie देखा है कभी किसी ने? So similarly, in this, you will once you set your eye, you will be able to see in a 3D vision any area. And then why we want to do this? Because it gives you a bird eye view of any area. Then you mark different river terraces. You can mark different alluvial fans. Then you click in that area. You can mark the fault. We'll do a small exercise in which you will just see the anaglyphs, and we will put the PPT, and then we will provide. So, and in some areas, if you want to find a active fault, nowadays people also use drones. Drone survey can be done. So with the help of drone survey, you know that you can generate contours, very high dense contours. Contour interval of let's say 2 centimeter or 3 centimeter can be generated using a drone. But on the other hand, like the Google Earth or other, topographical series, the contour interval is on the about 20 meters. So that's why the use of drones in geology nowadays increasing, because you need to do a lot of surveying. If you need high precision cloud point, then you need to use the drones. And drones are also used to mark active faults. You know, you can mark a active fault because on an area, if you have a high resolution dam, then you can clearly see from where the fault is passing. It helps you a lot. But in order to fly a drone, you need a license and you need to do a lot of paperwork, and then only you should fly a drone. And there are some areas where you cannot fly drone, so you need to check those areas, where we can fly drone. Okay. So now what we will do is we will show you some remote sensing data in which you can see 3D. Okay. If you have any question, you can ask. Otherwise, we can go for the other practical. Yes. No, no. So this, yeah, what we have done is, yeah, you can measure the length from here, right? But when you are doing it, this exercise in the software, like yes, in the software you can measure the length by applying this. So if you follow this, then you can calculate the length in a software. Yeah, you can digitize. Yeah, you can digitize and you can calculate the length, because these exercises can be done easily in computer, but we have made it print out for you so that you don't need a computer. But otherwise, all these morphic metric indices, you need like software, RGS, MATLAB. So you can do these exercises on a computer. Okay. Okay. So now we will show all the students can wear the glasses, and you can have the depth perception, stereographic view of the. Yeah, we can put the computer here, and students can come one by one, and or maybe in a group of two. We can put here also. So okay. So you can come wearing the 3D glasses. If you have glasses like this, then you need the overhead glasses, and then you can have a look at the this anaglyph. Ashok, Aju, you can come. Yeah. इसमें देखो जरा लगा के आप what you are able to see 3D perception and if you see here maybe you were able to see some. Now maybe you can see this. Now, sir, if you focus in this figure, then you will be able to see a tectonics curve basically. And you can also see close to the river, various river terraces are present. You can see along this very river. There are river terraces. You can see the elevation of these river terraces is varying. So what you can do is on computer basically you can mark the different geomorphic features. Okay. So uh, these photographs basically helps you to geomorphic maps of the area. If you want to make large scale geomorphic maps, or you want to uh, mark the faults or lineaments on the topography, then these maps helps you a lot, because not everywhere you can go. But so we have made these geomorphic maps of this area using this remote sensing data. हम्म, ठीक है। जी, हाँ, इसको यहाँ पे बताओ थोड़ा सा, यहाँ पे जैसे रिवर टैक्सीज देख सकते हैं ना, ऊपर नीचे, ये शायद डेप्थ परसेप्शन दे दे। देखना क्या है, देखो इसमें तुम्हें यहाँ पे देखना है कि अगर आपका जो है, यू आर एबल टू सी इन 3D, you know, you are able to see something in 3D, like you can see here the river terraces. So are you able to see the depth perception? किसी भी एरिया में जूम करके देख सकते हो आप। You are able to see this fault, डेप्थ परसेप्शन आ रहा है आपको? ये देखना है आप, देखो इसको। नहीं नहीं, यहाँ देखो, रिवर के पास देखो, देन you should try to see close to the river, and whether you are able to see the some elevation or steps। खुद आगे पीछे हो जाओ, ऐसे ऐसे कर सकते हो, अपने अपने आप को करना है, कंप्यूटर को नहीं। यहाँ पे देखो, तुम्हें डेप्थ परसेप्शन आ जाएगा। इस ऊपर दिख रहे हैं ये घर, ऊपर को उठे हुए हैं। Then once your eye is set, then you can see the whole area into 3D। बट जब तक आपका आई परसेप्शन नहीं आता ना, तब तक वो 2D प्ले फिगर ही दिखेगा। बट वंस योर आई इज सेट, देन यू कैन सी द डिफरेंस इन हाइट, एलिवेशन का जो डिफरेंस है वो दिखना शुरू हो जाएगा आपको। दिखा? कुछ नहीं दिखा, कोई बात नहीं। नहीं, मुझे तो दिख ही जाएगा। हम्म। जैसे यहाँ इस तरफ आप देख सकते हो, ये ऊपर है, ये नीचे है, ये ऊपर है, ये नीचे है। ऑन ही, अच्छा हो गया ऑन, ठीक है। हम्म। नहीं, आपको ये देखना है, जैसे यहाँ पे देखो, ये ये जो अलूवियल फैन है, दिस इज रेज्ड। सो हाँ, यू जस्ट ट्राई। डेप्थ परसेप्शन नहीं आएगा तब तक आपको कुछ नहीं दिखेगा, 2D ही दिखेगा, 3D नहीं दिखेगा। ठीक है। जैसे अभिषेक, मेरा जो पीएचडी स्टूडेंट है, उसको 1 साल तक दिखा ही नहीं कुछ। उसके बाद उसको समझ में आएगी क्या देखना है, इट टेक्स टाइम। So this cartosat data basically we purchase from National Remote Sensing Center, and we have lot of scenes of Himalaya, and you can there is a software known as NV, in that you can make anaglyph, and then you can have a 3D depth perception of the area. So this helps you to map large areas, and then once you have identified a fault, then you know where to go in the field. You will take a car, or you know where to go, where to do the field work, because then in the field you will see where is the fault. So before we go to the field, we plan our field, where we want to go, where we want to stop, what we can expect to see in the field. Okay. So in this image, I think we can show you. In this image, the Yamuna Tier fault, you know the Yamuna Tier fault is also visible in this image. You see, Are you able to see this line? You see this line here? This line is there, and this small rivulet is shifting. So basically, when I was telling you, right? I was telling you that we have put a trench across a Yamuna tear fault. So in this image, this is the Saton landslide right here. I was showing you in the morning. This is the Saton landslide. You saw in the morning. So now, if you see this image, you know, if you just little bit focus, you able to see this linear. You see this linear line. You were able to see, and then there is a river which is coming like this. Now it is deflected right here where the fault is there. So what we have done is we trace this fault in this river, and where we will put the trench. So in the trench, when we put the trench, we can see that one layer is coming like this, and there is a totally different rock across the fault. You know, so this remote now you can see this is a jungle. If you go in the jungle, you will be not be able to figure out what is a fault. Because you will see trees, leaves, because you cannot distinguish that something is linear is passing through this area. But with the help of remote sensing data, high resolution data, you can see the lineament. And actually, this is an active fault. We have dated this fault, but we have not published it, and we will publish it soon. Okay. So this is the first trench on the Yamuna Tier fault. Before that, people were talking about that, yes, there is a Yamuna Tier fault, but they have not marked or they have not put a trench on the fault. So we have put the trench on the fault using this data. you know so in our in geology, basically, if you have a trench on a fault, because then you can get more information, from the fault. So you can see clearly a live example where this fault, this remote sensing data, and secondly, you can see other faults, you know these faults which are intersecting the small landslide. And then you can also see the this bigger scarp. You see this scarp, we saw that in Google. So if you see carefully, this is the scarp of this Satongad fault. This is following like this. And there is a Sirmaur College on top of this back hill facing scarp. So now you see this, right? You are able to see now the scarp is very clearly visible. So this is again is a example of tectonic scarp. Now the question is, so many people are living in Dehradun, close to Missouri, and we have so many faults which are present in the very vicinity of a huge population. So these are very important questions, for geoscientists to understand. So all these alluvial fans, you can see these different alluvial fans. These are very old alluvial fans. So all this material is eroded and deposited in this Pinjor Dune, and people, stay in these areas. So there are, you can see this fault is coming in this valley. So a lot of these geomorphical features or lot of these topographical features which we see, they have evolved through time, right? They have evolved through time, and we need to understand what's what's going on in the area. Okay. So now you can spend some time looking at these pictures, and it takes some time to see the 3D perception. Once you have it, then you will not lose it. I mean, you will understand, okay, I can see the 3D in this. Okay. Okay. Thank you.